High above the Columbia River, a colossal concrete arch stretches across the gorge, holding back a reservoir nearly 250 square kilometers in surface area. Deep beneath the bedrock, where the river once carved its natural path, immense concrete tunnels descend, each roughly 12 meters in diameter. Within these confined spaces, water, weighing hundreds of thousands of tons, accelerates to incredible velocities. It then slams into a machine that is, in essence, a giant pinwheel, a turbine with blades weighing many tons each, machined with micrometer precision. The entire structure, from the spillways to the submerged generators, vibrates with a low, resonant hum. This is the sound of immense power being generated, harnessed from the sheer force of water falling from great heights. These aren't just any generators, they are the heart of our electrical grid, powerful enough to illuminate entire cities. Yet, despite the staggering forces at play, the millions of liters of water, the monumental weight of the rotating components, these immense machines, these multi-story Francis and Kaplan turbines, spin at an astonishingly precise, unwavering speed. They spin at exactly one speed, forever. This seems counterintuitive. Imagine pushing a heavy flywheel. The harder you push, the faster it spins. Or consider a car, press the accelerator, and the engine RPMs climb. But a hydropower turbine, generating electricity for a nation, cannot fluctuate its speed. Its rotational velocity is locked, immutably, to the very rhythm of the electrical grid it feeds. The question then becomes, why? Why do these massive, water-driven behemoths spin at precisely 10 to 14 revolutions per minute, or sometimes 60, or 72, but never 11, never 15? And how do engineers achieve this impossible feat, maintaining absolute rotational constancy when the demand for electricity fluctuates wildly, when river flows change, when millions of homes suddenly turn on their lights or factories power down for the night? How do they control a force of nature so vast that it can literally reshape a river, making it obey an invisible, electrical pulse? The answer lies in the fundamental physics of the alternating current grid itself, and in an ingenious control system known as the governor. Electricity in a large grid is not a static commodity, it's a dynamic, pulsing phenomenon. In North America, this pulse beats 60 times a second, 60 Hz. In Europe and much of Asia, it's 50 Hz. This frequency is not arbitrary, it's a critical parameter that dictates everything from the speed of electric motors to the performance of electronic devices. If the frequency deviates too much, even by a tiny fraction, it can cause widespread instability, damage equipment, and lead to blackouts. And this frequency, this fundamental heartbeat of the electrical grid, is directly tied to the rotational speed of the generators producing the power. Large hydropower turbines are what engineers call synchronous generators. Their rotors, massive assemblies of electromagnets, are designed to rotate in perfect lockstep with the grid frequency. Let's break this down. A generator works by rotating a set of magnets, the rotor, past coils of wire, the stator. As the magnetic fields sweep past the coils, they induce an electric current. The faster the magnets spin, the more frequently the magnetic field lines cut through the coils, and thus the higher the frequency of the generated alternating current. However, the relationship isn't simply linear, it's also determined by the number of magnetic poles on the rotor. Imagine a bicycle wheel with magnets around its rim. If it has two magnets, one north and one south, it completes one full electrical cycle, 1 Hz, for every revolution. If it has four magnets, north-south, it completes 2 cycles per revolution. For the electrical grid to operate at 60 Hz, and for the generator to be synchronized, its rotational speed in revolutions per minute is dictated by this formula, frequency x 120, number of poles. Take, for example, the turbines at the Grand Coulee Dam, some of the largest Francis turbines in the world. Each of these units can generate over 800 megawatts. They have a specific number of magnetic poles, let's say 32 poles for illustration on a 60 Hz grid. Applying the formula, 60 Hz x 120, /32 poles equals 225 revolutions per minute. This speed, 225 revolutions per minute, becomes the fixed, immovable target. If the turbine spins even slightly faster, it pushes the grid frequency up. If it slows down, it drags the grid frequency down. Both scenarios are problematic. So, the core problem is this: how do you get a colossal water turbine, connected to a reservoir holding billions of liters of water, to spin at precisely 225 revolutions per minute, or 10 revolutions per minute, or 72 revolutions per minute, depending on its specific design and pole count, when the amount of power it needs to produce is constantly changing? This is where the governor system enters, acting as the ultimate maestro of the water flow. Forget the common sense notion that you simply turn up the water to make more power. That's true, but turning up the water also tends to make the turbine spin faster. The trick is to increase the power output without increasing the speed. The primary mechanism for controlling the water flow into a turbine is a series of adjustable gates called wicket gates. These are like a ring of Venetian blinds around the turbine's runner, the part with the blades. By opening and closing these gates, engineers can precisely control the volume and velocity of water impacting the turbine blades. When the electrical load on the grid increases, when millions of people turn on their lights, or a factory begins a shift, the grid demands more power. If the turbines can't supply it, the frequency will start to drop. The governor detects this minuscule drop in frequency, often measured in hundredths or thousandths of a hertz. This tiny deviation triggers a hydraulic servo mechanism, a complex network of oil pumps, valves, and pistons. This system then very slowly, very precisely, opens the wicket gates a fraction of a degree. More water flows, increasing the torque on the turbine blades, and the generator pushes more power into the grid. But here's the crucial part: as the wicket gates open, the governor doesn't just let the turbine speed up. It is constantly monitoring the actual rotational speed of the turbine shaft. If the increased water flow starts to push the speed above the synchronous target, say, 225 revolutions per minute, the governor slightly reduces the wicket gate opening, counteracting the overspeed. It's a continuous, dynamic dance, a feedback loop that constantly adjusts water flow to precisely match power demand while holding shaft speed absolutely constant. Imagine trying to keep a car engine at exactly 2000 revolutions per minute while driving uphill and then downhill, simply by adjusting the fuel pedal. That's essentially what the governor does, but with forces far greater than any car engine. Which of these machines would you least want to be standing next to as it operates at full power? Tell me below. Conversely, when the demand for electricity drops, the grid frequency might try to rise. The governor detects this, and its hydraulic system subtly closes the wicket gates, reducing the water flow and thus the power output. The turbine still spins at its exact synchronous speed, but it's now doing less work. This is the central paradox and the elegant solution: the governor doesn't control speed directly by trying to slow down a too fast turbine, or speed up a too slow one by brute force. Instead, it controls the power output of the turbine. By carefully modulating the power, it ensures that the turbine is always doing just enough work to stay in perfect electrical synchronization with the grid. A common false belief is that these turbines have a massive braking system, like a car's, to control their speed. Everyone assumes a machine that heavy, with that much rotational inertia, must have colossal brakes. The engineers, however, do the exact opposite. They don't use mechanical brakes to regulate speed. They use the water itself. When a turbine needs to be stopped for maintenance, or in an emergency, the wicket gates are completely closed. The flow of water is cut off. But the turbine, with its immense mass, doesn't just stop. It continues to spin for a very long time, sometimes for hours, slowly decelerating due to the friction of its bearings and the resistance of the air and water around its blades. If an actual mechanical brake were applied to a turbine spinning at operating speed, the forces involved would be so destructive that the brake pads themselves would likely vaporize, and the turbine shaft could be severely damaged. The entire structure would shake violently. Instead, the kinetic energy of the spinning turbine is dissipated naturally, or in some cases, the turbine can be braked by applying a reverse magnetic field to the generator, turning it into a giant electromagnetic brake. This method is far gentler and more controlled than any mechanical friction brake. The actual trick, the elegant synthesis that allows these immense machines to spin at one exact speed forever, is a continuous feedback loop. The synchronous generator must run at a speed precisely dictated by the grid frequency and its pole count. Any deviation is detected immediately by the governor. The governor then makes tiny, calculated adjustments to the wicket gates, modulating the torque applied by the water to the turbine blades. This ensures that the generated power always matches the grid's demand, keeping the generator in perfect electrical and mechanical sync. It's a delicate balance, a continuous negotiation between the raw power of falling water and the precise, invisible pulse of the electrical grid. These incredible feats of engineering, the precise control of millions of liters of water, the synchronization of multi-ton rotors to a fraction of a hertz, are often hidden from view. Yet, they are fundamental to the stability and reliability of the modern world. Every time you flip a light switch, or your computer hums to life, you are indirectly tapping into this invisible symphony of precise engineering, a constant dance of water and electricity, all orchestrated to the beat of an unyielding, fixed rhythm. The machines that move the modern